Hello, my name is Charikleia Pappa, and together with Mr. Emmanouil Vougioukas, Nikos, and Lagaros, we have conducted a comparison for the offshore and onshore wind turbine foundations. It is worth mentioning that both onshore and offshore wind turbines feature prominently in the world's energy source mix, and this is evidenced also by the studies published in scientific databases such as Scopus and Web of Science. The leap of the construction of wind turbine farms fosters the exponential optimization development of the wind turbine as a system, including the upper structure, the wind tower, which includes the tower, hub, and the blades, along with its foundation. In contrast with the mutual contribution by both onshore and offshore wind turbines in energy production, with the onshore wind farms accounting for 81% of new capacity in Europe 2021, with Sweden, Germany, and Turkey holding the privileged position, and China for 80% of the global offshore wind capacity added in 2021. Most optimization studies conducted so far on wind turbine optimization are performed focusing on the wind farm layout optimization, and especially for the offshore wind turbines. As far as the onshore wind turbines is concerned, after the collapse of the wind tower due to the typhoon in Taiwan, there was a study in 2010. They were studied the critical mechanisms that need to be secured so as to avoid another such case. Codes, structural elements, historical wind speeds, and construction records were examined by a risk management perspective, while others have tried to modify the current International Electromechanical Commission design standard and trying to set new directions to protect irreversible failure of wind turbine extreme wind conditions such as typhoon and hurricane. It is proved that the conical raft design of onshore wind turbine foundations improves the resistance of the soil structure interface and gives a significant decrease in tilting compared to a flat circular raft. Consequently, the dimensions of the foundation are decreased, and this leads to potential cost reduction. Steel monopiles, which are mini piles made by steel and are used especially for shallow foundations, are proposed to improve the shallow foundations of the wind tower systems and lead significant reduction of dimension and as a result reduction of cost of the foundation. It should be mentioned that the global renewable energy generation capacity has increased from 1,829 gigawatt in 2014 to almost 3,000 gigawatt in 2021, while the power generation cost has decreased from 0.029 USD to 0.033 for onshore wind turbine foundations. There are some attempts to improve the onshore wind turbine foundations. There was proposal for the removal of all vertical stirrups, the shear reinforcement, including those placed for shear reinforcement and those allocated in the ring of the foundation for load distribution. Proposal also was for the removal and replacement of 50% of radial and circumferential rebars with metallic fibers dispersed in the concrete mix. It was proved that targeting to bigger hub heights of the wind turbine is not connected to higher electricity generation. There is a certain hub height that enables wind turbines to deliver the lower cost electricity, and growing beyond that height does not pay off the rise in capital investment and expenditures needed for stronger foundation and taller and sturdier towers. This refers to the wind turbine and how it affects the foundation. Despite the trend to optimize the heavy machine tools foundation over the last years and taking into consideration the determinant role of the foundation on the wind turbine balance, more operators tend to be risk averse and abstain the implementation of optimized foundation design methods. Concerning the attempts to improve the onshore wind turbines foundation, there was a study concerning the role of soil foundation and structure interaction, leading in the optimum inclination of the patterned piles of the foundation in the case of pile foundation of wind turbines. Gravity foundations are preferred when they are possible to be used, as they are of high strength and they can have the desired shapes of needed design. Usually, the foundation dimensions of the wind turbines are provided by their suppliers. The foundation acts as cantilever, resulting in high thickness in the center varying from 2.5 to 3 meters and getting thinner at the edge close to 0.4 to 4 centimeters. Meanwhile, wide research was carried out on the onshore wind farm seating optimization, proposing methodologies that can be applied over regions worldwide so as to utilize the complementary potential of distributed wind energy, identifying also the distance between the wind turbine foundations at a wind turbine farm. The wind turbine seating optimization also included the topography characteristics such as slopes of the terrain. As far as the offshore wind turbines categories is concerned, there are two main categories: the fixed offshore wind turbines, which is for lower depths, and the floating offshore wind turbines foundations, which is appropriate for deeper water. Concerning the fixed offshore wind turbine foundations, the first category is the monopiles, which are usually used for 10 to 15 meters depth. The monopiles are currently the most predominant type of foundation for offshore wind turbines around the world. This is because of its shape. The monopiles are circular, and as a result, they are easier to design and to be analyzed rather than other foundation types. Also, due to its shape, the water resistance is reduced, and they are founded in the seabed. Additionally, since they are one of the oldest ways for offshore wind turbines foundation, this gives them the advantage of acquiring mature supply chains, and they can be mass produced and transported through vessels to be installed. So this is the first category. The second category is the jackets, which are used for depths from 40 to 100 meters. They are usually preferred as they are more tolerant of varied geotechnical conditions and can be used in deep water due to the fact that they are stiffer structures and require less steel than monopiles for deeper water locations. On the counter side, they are more complex and require labor intense to fabricate and install than the monopiles. The next category is the gravity-based structures, which is the oldest type of foundation, as their design is based on the counterweight that is needed to balance the forces applied on the offshore wind turbine. They are used for depths from 15 to 40, and due to their stability system, it's needed high quantities of materials, and in order to achieve this stability, and this is the reason that makes them very expensive for deep water sites. The fabrication and installation requirements are totally different to other fixed bottom foundations. The next category is the tripos and tripiles, which are not regularly used as they have been proven to be not very cost effective for offshore wind turbines. The next category for fixed offshore wind turbine foundation is the suction bucket. The suction buckets are usually used for depths around 10 to 55 meters, and they require very specific seabed conditions as they are not drilling deep into the seabed, but they are more surfacial. This gives them also the advantage of being able to be fully removable at decommissioning of the wind turbines, while the monopiles or jackets are typically cut off just below the mud line. After we have seen the fixed offshore foundations, wind turbine foundation, we will check now the floating offshore wind turbine foundations. The first is the semi-submersible floater. The semi-submersible floaters are commonly used for depths around 40 meters. The structure consists of multiple columns which provide hydrostatic stability and of multiple pontons which provide buoyancy. The above elements are held into place by catenary or tone-spread mooring lines, and there with drag anchors which lead the seabed. The motion of the semi-submersible floater is a salient design challenge, but this disadvantage is counterweighted by the fact that it can be used for various depths. The next category for floating offshore wind turbine foundations is the spar floater, which consists of a large spar, which is a draft floating cylinder with a low water plane area, which is designed to keep the center of gravity below the center of buoyancy, so it can be ballasted. The spar relates to catenary or tone mooring lines, and these relate to drag or suction anchors which reach the seabed. Comparing the semi-submersible floater with the spar floater, the second has better stability and its design is simpler, but the fabrication, transportation, and installation are more challenging because of its tall structure. The spar floater is usually used for depths around 100 meters. The next category is the tension leg platform, which is a vertically moored platform. It consists of columns and pontons, and it is used for depths around 40 meters. Its advantage is the mooring system, which consists of vertical tendons which restrain the heave motions. Also, due to this, it has good stability and can be used in a range of water depths. On the other hand, the tension leg platform is literally compliant and will surge, sway, and yaw, while its construction and anchoring system are of high cost compared with other floater designs. The next type is the barge platform, which can achieve stability using their distributed buoyancy, taking advantage of the large waterplane area. This type of floating structure is usually distinguished by a rectangular annulated-shaped floating substructure with a pool at its center, which diminishes the floater motion by absorbing the wave loads. The suction anchors are designed to bear all design loads such as dynamic loads from waves and current and wind turbine generated loads, installation and removal loads from suction, over pressure and leveling. The anchor foundations or mooring of suction anchors, fluke anchors, pile, gravity and plate anchors also follow all the specifications for floating wind turbine structures. The advantages of floating offshore wind turbine foundation is that, first of all, they significantly increase the age of wind farms, allowing installations for over 200 meters. They take advantage of 58% of offshore wind resources in deep water. The wind turbines parts, like turbines and bases, can be assembled in port, then towed to site for installation, while the maintenance can also be done in port by towing the turbine back to port. They minimize the risk to migratory birds. There is less visual impact on shore. They certify safe operation under extreme pitch, roll, and heave wave motions. There is stability in design and dynamic coupling of traditional rotational platform motions and turbine motions. The dynamic behavior of mooring lines is also better. Buoyancy to support full height of turbine tower and platform, and the anchoring system mooring ballast and buoyancy factors dependent on spar, tension length platform or semi-sub. The disadvantages of floating offshore wind turbine foundation is that the cabling to affix the platforms of the floating wind turbines in planes requires ongoing and thorough inspection and maintenance. The anchors and cabling which consist the wind turbine foundation can disrupt the sea life. Since the floating wind turbines are towed to site, the possibility of invasive species introduction is increased. As we see between onshore and offshore wind turbine foundations, it is proved that offshore wind turbine foundations have been excessively studied and a lot of optimization efforts were conducted, while onshore wind turbine foundations are mainly based on the typical cantilever approach. Both types could be further studied so as to lead on cost reduction while maintaining or enhancing the functionality of both. Thank you for your attention.